So this one-way ANOVA, again, like all other sessions, we will learn the basic concepts, then research questions, assumptions and hypothesis, commands and interpretation, and the summary. So this one-way ANOVA, it is known as the analysis of variance. So that term only says that we are analyzing variance, and it is also known as the between subject ANOVA, one factor ANOVA. In this, we compare the means of more than two groups. So independent sample t-test, we were having two groups, like group 1 and group 2. In this case, you are having more than two levels, and there you can, that's why you have to do this post hoc analysis also, where you compare the difference between the group, like group 1 and group 2 and group 3, etc. So post hoc analysis. So now what are the research question? Again, it is a similar research question that there will be a, again, the internet connection is going unstable. Okay, is it okay? I thought. So what is the difference? The group will be more than, you can see there are more than two groups here. So if I want to compare the difference in the mean BMI score across the three levels, maybe the black, white and others, there can be one thing like, is there any difference in the post-operative pain score across surgical technique 1, 2 and surgical technique 3, or the student satisfaction level differs across the various teaching technique, and the three teaching techniques are the lecture, demonstration and case-based learning. So in all these things, what we have observed, that there is a scale variable in each research question, and I am comparing the average of this value across three or more levels of a categorical variable. So just remember, independent sample t-test, we were having two groups. In ANOVA, we are having more than two groups, and that can be like 3 groups, 4 groups, or more than 2 groups. So appropriate statistical test is the one-way ANOVA. So 3 research designs which are possible, and this we have seen in the independent sample t-test also. So the first was the mean difference between 3 groups. So you can see here there are 3 groups. Gender, you can see there is a male, there is a female, and there is a transgender. So there are 3 levels here. And if I want to compare the mean cholesterol level, which is a continuous variable across the male, female, and transgender, then I can apply one-way ANOVA. The other 3 research designs, the other research type of research design could be, if I want to see the mean differences between 3 interventions. So like there is a group and you have got 3 groups. There is a group of people where the intervention is through diet. There is a group of people where the intervention is through exercise. And then the third group is the control arm. So you can see here, this I am talking of control arm, this one. This is the exercise group. And maybe this is the diet group. So there are 3 groups, and this is the value of the blood cholesterol, which I measured after 6 weeks of all these 3 intervention: exercise, without any intervention, and diet. So the third type of research design could be, if you want to see the change in the mean score or the mean difference in the change score, like we have seen in the independent sample t-test. So here you can see there is an intervention which is diet, like the previous one, exercise and control, and you have got 2 measurement here, paired value, before and after intervention. So it is the before intervention cholesterol level, this you can see, and this is the after intervention cholesterol level, and this is the difference. So if you want to see whether there is a change in the mean score between these 3 groups, again, between the diet, one group, exercise, and this control, and in this case, we will be doing this difference. So we are going to compare the change score, this change score, this one, and then control. So these 3 we are going to test. Then also we can apply one-way ANOVA. So what are the underlying assumptions of this one-way ANOVA? So the first assumption is that the dependent variable, it should be continuous. Like in this case, you have seen BMI level, serum cholesterol level. So they are continuous in nature. Then the independent variable, it should be a categorical variable, which should have more than two categories. And there should be independence of observation, means the categories should be independent of each other. Like all assumptions we did in the independent sample t-test, these are the same interventions. The fourth intervention is that the dependent variable, it should be normally distributed across the categories of the independent variable. This also we tested in the independent sample t-test. There should not be any significant outlier in the dependent variable, and there should be homogeneity of variance. That means the variances in the categories of the independent variable, we assume that it is all the three groups they are having from those population from which we have withdrawn these samples, they are having the equal variance. So the hypothesis is that there is no difference in the population mean of the group. And then in the alternate hypothesis is that there is a difference in the population mean of the group. That means at least one of the group population mean is not equal. Now let's understand the concept of variance. And there are two types of variance which we discussed: within group variance and between group variance. So for to understand the within group variance, this is an example like you have taken 500 black individuals. So this first column, it tells you the serial number of people with the 500 subjects. And race of all these are black. So all these belong to one group. And this is the BMI. So you can see the range, it is 18.1, various BMIs are there. Similarly, there is a white people also, you have taken white individual also, and you have calculated. So this is the frequency. So you have got something of this graph. So you have made the frequency type table like this, and this graph here, this is the BMI of black. It is not the white one. Sorry, this is black here. So this is the within group variance. Variance, remember the descriptive statistics, we studied variance, that it measures the dispersion. So this is the within group variance of BMI in black people. Now, similarly, if you see these three graphs, what are you seeing here? All of you. Can anyone explain this graph to me? Like there are three races: white, black, and others. What are these three graphs?
Null hypothesis.
Within the group, they are normally distributed.
So that means it is the within group variance. All the three graphs which you are seeing now, this is the within group variance. This is the within group variance among the white, in the black, and this is, we are seeing BMI. And this is a BMI value. So if you calculate the variance in one group, this is known as the within group variance. Is it okay to all of you? So you will have three variances here, three within group variance. So for each group, we have to estimate the value of within group variance. So like these are the three graph, you can say this is black, this is white, and other race. So consider a hypothetical situation. You have measured the 500 BMI of 500 people from each race. So can you subjectively say that out of these three, which group has got higher variance?
Other race sample.
Yes, it's like because it's a spread, that horizontal spread is more. So that's why we can say that variance of the other race is more. But it is a subjective way by seeing the spread. There are objective way to measure this variance. So now this was the how to measure this objective variance. So now first this is the, if from the mean, if there is a mean of black people is 20, this BMI, white is 22, and others is 24. So now within each group, you subtract the individual values from the group mean. That we did in the descriptive also. We'll get a value and then we'll square that. Like in this case, you can see this is the 20. This was for the first group, this black one. So this is 20. So we are just showing you with one example. So you can see the difference. So this is 14. So this will be plus 6. This will be plus 7, minus 3, minus 6, and minus 4. But if you square it, everything will become positive, and then you sum it up and then you divide it by n minus 1. That will give you the within group variance. So the difference value simply tell you how far the individual value is from his or her group mean. And if you square it, this will be the variance. Similarly, that's why we call it as a sum of square value. And we did it in the descriptive also. In this way, we can calculate the variance of white individual and variance of the other race, and then we can compare them objectively. So this was the concept of within group variance. So if the individual values in a group, they are very far away from the group mean value, then the group variance will be high. And if they are very close, then the group variance will be low. Similarly, you can calculate the group variance by subtracting the group means from the overall mean. That means there will be an overall mean. Like if you take the mean of the white, mean of black, and mean of others, that will be overall mean. And then you subtract this group mean from the overall mean, square it and divide it by number of group minus 1. This will be a between group variance. Now let's see how to do this. So you remember the group mean of black was 20, group mean of white race was 22, and group mean of others was 24. So overall mean is 23. Now if I have to calculate the between group variance, what I'll do, I'll subtract this group mean from this overall mean. So it is plus 3, plus 1, and minus 1. And then we have squared it, and sum of square will be 11 divided by total number of groups in this case. So there are 3 groups minus 1. So the variance, this within group variance will be 5.5. Is it clear to you, these two concepts? Between
Yes,
group variance
Yes, ma'am.
and within group variance.
Yes, ma'am.
Okay. So if it is clear, so in this case, again, the same concept. If the group mean values are far away from the overall mean, then the variance will be high. If the group mean value is very close to the overall mean, there will be less variance. So now what is this F statistics? In ANOVA, you will always see there is something known as the F value. So the ratio of these two between group variance and within group variance is the F value. Is it clear what is F? So when you take, if you can recall the example of between group variance and within group variance, so between group variance divided by within group variance will be the your F value, and under null hypothesis, it will give you the F statistics. This value is 1. So you may get a typical situation like the first situation. There will be high between group variance and high within group variance. So this has been drawn like with a sketch pen and pen. So don't think that we have, like this is just a hypothetically drawn curve. So here you can see that both the variances are high because the spread is more, and this is also like distance is more. Similarly, this is again high between group variance but low within group because this is narrow. So there is a low within group variance. This is another example where there is a low between group variance because these are overlapping. So the within group variance is high, but between group variance is low. And this is another graph where both is low because this is narrow and they are overlapping. So low between group variance and low within group variance. So now again, let's understand the concept of variance with the graph. The same thing. If you see this, here you can see the 3 means are very close to each other. So that means there is a low variability between groups, and variability within groups are same because shape of the graph is almost same. Here you can see that the three means are farther from each other. There is a high variability between group, but variability within group is the same. So now how we do the homogeneity of variance testing in, although it is written SPSS, the same is there with the JAMOV. So we take the variances of population from where we have drawn the samples and we test that it should be equal. And this is the assumption of this Levine's test of equality of variance, which we have learned in the independent sample t-test. And the same concept holds true here, that if the value is more than 0.05, we say that the assumption of equal variances is met. So this JAMOV also produces two types of independent F statistics. If the equal variances is assumed, then we use standard F statistics, its degree of freedom and the type of post hoc, because there is a three group. So you compare the values also, like between 1 and 2, 1 and 3 and 3 and 2. So you do the post hoc comparison. So that's why the type of test which we have to apply, because there are various post hoc tests. So if the homogeneity of variance is met, then we will apply the Tukey's post hoc test. If the homogeneity of variance is not met, then we take the Welsh ANOVA, like we used to take the Welsh T. Similarly, you have to take Welsh ANOVA, and the type of post hoc which we have to click is the Games-Hobble post hoc test. Now, understanding the concept of post hoc test. What is this post hoc test? So post hoc test is basically the comparison. We elicit the difference in the two groups and whether that difference is statistically significant or not. So just to simplify this, let's understand this with an example. So there are three money banks and three kids, they have planned to break their money bank. And in this, they have decided, they have set one rule. So they have said that if difference of the amount between the two money bank, if it is more than 500 rupees, then it will be considered significant. So we assume that all money bank have equal amount. So now, what is our interpretation? In first case, you have got 150 rupees in first, 190 rupees in second, and 250 rupees in third. So what is your interpretation? Any significance, a difference is there or not? You have to type in the chat box, yes or no.
No, ma'am.
No. Yes, because it is, the difference is less than 500. Now, what is your interpretation? And if there is a difference between which two money banks? A and C. Venkatesh is answering. All other participants? Yes. So 1 and 3. Because the difference is more than 500, it is 200 and 800 is 600, which is more than 500. What about this now?
1 and 3, ma'am.
Between 1 and 2 and 1 and 3 also.
Yes.
1 and 2.
And finally this?
All the differences are significant.
Yes. So 1 and 2, 1 and 3, and 2 and 3. All are significant. So in Way ANOVA, we are comparing the means of more than two groups. That's why the concept of post hoc is there. So if there are three groups, then F statistics will be calculated using three pairs. So we compare like A, B, BC, and AC. And if there are four groups, we compare the F statistics using 6 pairs. So you will get a significant F statistics even if the mean values of only one pair differ significantly. It is not necessary that all post hoc will be significant. Even if there is a one group which is significant, you may get a significant F value. So if you are having a significant F value, you should always look for the pairs which is having that significant. That means you should do a post hoc test. Okay, so I'll go to this question now. चुप हो जाओ यार। So this is a question for one-way ANOVA. So I have to check the distribution of the following parameters and compare their mean values across the comorbidities category. And comorbidities, remember, in day one, we have made 3 comorbidity categories. Asymptomatic, mild, that was one category. Category 2 was of moderate. And category 3 was of severe. So I'll check these values. So I'll go to this data sheet. And then maybe I'll go to ANOVA and click on this one-way ANOVA. There are many other options, but we are clicking only one-way ANOVA. If you click this, there will be dependent variable and there will be option of grouping variable. So in the dependent variable, what we have to move, there are many. First in the grouping variable. So in the grouping variable, I have to, this one, total number of comorbidity, transform to, I think this is the data. Let me go and check the data, which is the variable here. So I'll go to the data. And because I don't, I think I have forgotten the levels, which I recoded. So you can go.
Ma'am, I think it will be disease severity.
Disease severity, let me check because there are 2 variables with this name.
Or maybe total number of comorbidities also. We have 3 levels there. No comorbidity.
That's right. More than 2. No, let double check. No, this is the transformed one. What is the variable in this case across the comorbidity categories? No, in this case, what is that variable? That may happen with you also because we tend to forget if we don't label it properly. Comorbidity should have 3 categories. I think this data sheet doesn't have it. SES, smoker, DM. This is
Yeah.
So
Next
disease
one.
severity you have put, ma'am.
And this one.
Asymptomatic,
Yes,
mild,
yes,
moderate,
this
and
one,
severe.
This one. Yes. This one will be the asymptomatic, moderate, and severe. Yes. So disease severity 1 recoded. This will be the group. So, or maybe comorbidities categories, if you want to see, you can have this total number, no comorbidity, 1 to 2 and more than 2. You can take any of these 2. It's up to you because you are the researcher, so you can take any of these 2. So maybe I'll again go to the analyze, ANOVA, one-way ANOVA. You can have the disease severity recoded, and then you can have this values like SpO2. So SpO2, and I am taking first value now because there are 2 SpO2, maybe SBP, systolic blood pressure, hemoglobin, BMI. So I may take the BMI score. So let's take first 2 or 3 because then the look of the table will be very heavy. So first I'll explain with these 3 variables. Now, before I go to the actual value of ANOVA, first you have to test this QQ plot. You have to do this assumption check. That is there. So you go to this. If you see the homogeneity of variance, you will see here that what is your interpretation of this homogeneity of variance for these 3 variables, whether it is met or not met.
All met.
So all met. So that means we don't have to go for the Welsh. So here it is, don't assume equal Welsh. So I have to assume equal. That is the, this is the Fisher. So it has got a equal variance. So by default, it comes as don't assume, because it is difficult to get this assumption true most of the time when you will actually, because we have modified the data also, when you will be actually doing it, many a time you will find that in case of an independent sample and in case of a ANOVA also, one way ANOVA, you will not met this variance. Okay, so don't worry for that. You just have to report the no Welsh one. So I have clicked this and I have unchecked this. And then you have to have a descriptive table. If you wish, you can have a descriptive plot. And then you have to come this post hoc test. So this, okay, this homogeneity, I did not see that QQ plot, okay. Let me, yes, this was the QQ plot of SpO2 and this was the QQ plot of SBP and for BMI. So it is approximately normally distributed. So we can apply this and then you go to the post hoc test. So there are two options. Can you see here? In SPSS, there are many options. So we get confused whenever we see that. But Jamovi has kept it simple. So in this case, since it is normally distributed and Levin statistics, we are seeing that it is of equal variances. In that case, I will use this Tukey's post hoc. This Tukey's post hoc test, where it will show you the mean difference, report significant, and then maybe flag significant comparison, because then it shows you the star mark. So now if you see, so this is the assumption check. This is the group descriptive, like it, you can see the value, mean value of SpO2 in asymptomatic or mild, in moderate and in severe with its standard deviation. This also you have to report. And then you can see the value of this F statistics with 2 degree of freedom. So it comes with 2 degree of freedom. One is for number of groups and this is for the total sample. And here you can see the value of P. So none of the difference was statistically significant. So then I think if the value is not significant, then you will find that post hoc is also not significant. So you can see here the Tukey's post hoc for SpO2 2. So there it was not significant. Similarly, the post hoc for SBP is also not significant and for BMI is also not significant. So although there was some difference in the mean value here, you can see there was some difference, but ultimately this mean difference was not significant. And this is how you will enter the result. So in this case, like maybe you can have mean and standard deviation of the all three categories. Maybe this is, maybe you can assume it as a asymptomatic and mild, moderate and severe. You can have mean and SD. You can give the value of Levin statistics, F value. You can remove this because ultimately this should not be there. It's a blank template where you will fill the values. F values, because F value will report with the 2 degree of freedom. So here you write 2 degrees of freedom and then you have to write the pairwise comparison. So you will write the mean difference in this and then maybe the 95% confidence interval of the mean difference. And the interpretation is like in one way ANOVA, it was conducted to determine whether the continuous variable, it was different with the different levels of the independent variable. And the participants were classified into 3 group or more than 3 group. And you have to give the sample size also for group 1, group 2 and group 3. There were outliers or no outliers in the levels, level 1, level 2 and level 3. You have to do it by the box plot. So I assume that you know it. And then this dependent variable, the continuous variable, it was normally distributed and the homogeneity of variance, the value of P, it was met. as assessed by the Levine's test of homogeneity of variance. And then you have to give the mean and standard deviation. So data is presented at mean plus minus standard deviation. And you can write then regarding all these three, like DBP, SBP, or whatever variable you take. And then if the post hoc is significant, you can write the post hoc. If it is not significant, you can write that the QQ post hoc was not significant. So this is the way you do the ANOVA. First, you check the assumptions. And if the assumptions, if the homogeneity of variance is met, you click this assume equal. And if this normality is there, then you go for it. Otherwise, if it is not normal, then in ANOVA, you will see there is a Kruskal-Wallis. So this is the option which we are not touching. It is again the same. If the data is not normal again, but this is like independent sample t-test. A slight deviation from normality you can apply because this is also a very robust test. So you can go with the ones this one-way ANOVA.
Ma'am,
Yeah.
ma'am, can you please quickly repeat, ma'am? We are struck actually. I mean, we are stuck with the proceeding.
Okay.
After doing
Yes.
homogeneity and quick plot, what should we do, ma'am?
Okay. So once you have done this, you check with this QQ plot. Let me uncheck this. Okay. Mean difference. This none. And then this descriptive, remove this. This don't. This was like that. Nothing was there. So what we do, like first we see the assumption check, that is the homogeneity and QQ. So if you see the homogeneity, you will see here that the p-value, it is more than 0.05. That means you have to assume this, that the Fishers, we have to see the equal variances assumed. So we have to check this. And then since QQ plot is normal, so you will apply this one-way ANOVA. Otherwise, if this is not normal, then you would have gone here and apply Kruskal-Wallis. But since it is normal, you will apply ANOVA. So for ANOVA, you want descriptive table because you want mean and standard deviation for under each category. You want mean difference also for the post hoc. So post hoc, in case equal variances, can you see here something is written in the bracket? Equal variances. So the Levine statistics tells you that it is of equal variances. That's why you click Tukey. You report this flag significant correlation and significance, and then you can see the table. This is the difference. So this is the Tukey's post hoc test. So it tells you the difference, like see the first group, this. So this tells you the mean difference between moderate and asymptomatic and mild. And this tells you the mean difference between severe and asymptomatic. Similarly, the same thing, if you see, this tells you the moderate and severe. That's it, because the severe we have compared it already. So these are the group comparison. But since there is no star mark, that's why it is not significant. Otherwise, here it would have p-value. You can see here they have not given the p-value. But had it been significant, they would have given it the star mark, like, significant or p less than 1 or whatever. So it was not. Similar case is here. And if you come down, this is again, none of the values are significant. And these are the mean difference, means that between these two groups. So group wise comparison is there. So in general, if the value of ANOVA is not significant, because here you can see that p-value is not significant, then there is no need to do the post hoc. Right? Did you get it, Venkatesh and the all other people?
Ma'am, if the p-value is not significant here, then it's we need not do the post hoc, right?
Yes. Okay. Ideally for you at this level it is okay, but when you will join in advance, then I may change my statement. So then don't get startled that I have changed my statement. But for basic data analysis, this should be the way, that if the value of p-value of one-way ANOVA is not significant, then there is no need for the post hoc.
Okay, right. Thank you.
Tesh is writing in Tukey's, if it's significant, can we ensure anything from its T statistics? I don't think so, because T statistics is not important here. In this case, it is the F statistics which is important. Okay. They've given the t value, but I have not. I have no exactly. I don't think so. T has got any other. Maybe in post hoc, depending on the distribution, you can apply this, but I have not used this. Maybe let me check this once. In what case can we apply this?